Good morning, everyone. So it's a pleasure to welcome Sebastian. Sebastian Goldt is an assistant professor at the International School of Advanced Studies in Trieste, Italy. The goal of his group is to develop theories of learning in artificial and biological neural networks. Sebastian studied physics at Cambridge and did his PhD on the stochastic thermodynamics of learning with Udo Seifert in Stuttgart. Before coming to Trieste in 2020, he then spent 3 years as a postdoc with Florent Cresella and Lenka Zideborova in Paris. He is one of the organizers of the conference series Youth in High Dimensions, and he was awarded an ERT starting grant in 2024. Thanks for accepting our invitation, Sebastian, and stage is yours.
Yeah, thank you very much. Good morning, everybody. And yeah, thank you for the nice introduction, for the invitation. It's really nice to join this very nice series of seminars. And yeah, what I'd like to talk about are some of the recent work that we've done in our group with a lot of collaborators that I'll introduce kind of along the way, trying to understand what neural networks really learn. Okay, and so this question of what neural network learn, it comes from the impact of deep learning and how it changed machine learning in some sense, right? Because obviously neural networks have changed sort of how we interact with computers, right? We can now use natural language to prompt ChatGPT to have it write our code, our emails, and what have you. But all of these breakthroughs, they've come about because neural networks have also changed how we learn from data, right? So the classical approach to machine learning, say if you wanted to classify an input like this image, would be to use a lot of domain knowledge, a lot of engineering, a lot of craft to design some kind of feature vector that represents this image, and then to feed that feature vector into some linear classifier, right? And then that would do the work of classifying the image. And that worked to some extent. But with neural networks, we've kind of taken out this intermediate step, right? With neural networks, we instead take a deep neural network, we let it act directly on the images and let it learn this directly from the data. Okay, so we dispense with the domain knowledge, we let the neural network learn its features and then learn the classifier on top of them end to end. So a natural question is then, what do neural networks actually learn from their data, right? Somehow this approach of implicit feature learning works much better than all of the hand-designed features that we had before. So what do neural networks actually look at, right? What did they find in the data that we maybe didn't? This question is as old as neural networks themselves. So if you look, for example, at the AlexNet paper from 2012, when Krzyzewski, Szyszewski, and Hinton kind of set the new state of the art on the ImageNet competition with a deep neural network, they actually show what they learned from the data. So in the last figure of that paper, they show these filters that they learned. These are the first convolutional filters of AlexNet. And the kind of surprising or interesting observation here is that we actually know these guys, right? These filters, they're Gabor filters, which were well known in computer vision since, I think, the 60s. And so the interesting observation here was that a neural network, so a deep neural network, trained with stochastic gradient descent on some interesting image data set, learned these filters by itself, right? There was no explicit bias here. These features were learned by the network from the data directly. And this is an interesting observation because it didn't just happen in this isolated instance, right? So here's a more recent example from another deep convolutional network, VGG11. We see the same kind of localized, oriented, bandwidth-specific receptor fields, especially in the early layers. Here's another example that I find interesting from MLP Mixer. That's a different architecture. It's a little bit like a transformer, very vaguely. The key point here is that it doesn't have convolutions. Okay, so it's a fully connected architecture. And yet, if you look at the first layer, the embeddings, essentially, you again find these Gabor kind of filters. Okay, and here are some recent references that discuss this phenomenon. So I don't want to speak maybe about universality, but at least there seems to be some kind of convergence here in the features that neural networks actually learn from their data across architectures. And so to me, that suggests that there's something actually in the data structure that these neural networks pick up across these different architectures, right? And so what we wanted to understand is what is it and how does that work? Also, by the way, if you have any questions, especially on Zoom, let's try to make this interactive. So just speak up. I only see parts of you. So yeah, I think the safest thing is just to raise your voice and ask your questions straight away. Okay, so if there's something in the data that drives the emergence of these receptive fields, we need to understand a bit better what is actually in the data. How can we characterize the data, right? There's many different ways you could do this. You could think about Fourier modes, wavelets, all these kind of things. The distinction that I want to use here is the distinction between Gaussian and non-Gaussian fluctuations. Okay, so you can expand any probability distribution, for example, the distribution over images, into its cumulants. Okay, you can do this, for example, by taking the log of the expectation of the Laplace transform, but that's not so important. The important part is that the cumulants of a distribution, right? The first cumulants are the mean and the covariance of the data. So these are, in a sense, the Gaussian part of the data, right? These are fully captured by a Gaussian distribution. In a Gaussian distribution, though, all the higher order cumulants are equal to 0. Whereas in real images, of course, these higher order correlations between pixel, the triplet correlations, quartet correlations, and so on, are really important, right? Images are not Gaussian. The higher order correlations are very important. And not just important to describe the images, but actually also important for the feature learning of the neural networks. In fact, I'm going to argue that the features that neural networks learn are directly shaped by the higher order correlations. You can see this in two ways, okay? The first is what I would call a static perspective. You can take an algorithm that actually looks for the most non-Gaussian projections of your data. That algorithm, it's called independent component analysis. It's an old idea from the 90s. And just like PCA, principal component analysis, looks for the directions which have the most variance of your data, which capture the most variance, ICA looks for the projections that are the most non-Gaussian. So you define some kind of measure of non-Gaussianity, for example, the excurtosis, and then you find linear projections that maximize it. And if you do that on images, here's an example from Pierre Rabelin, from Ernest in Paris, you actually find something that looks a lot like these Gabor filters. Again, you get localized features, oriented filters with some kind of specific bandwidth. That's kind of a static argument, right? So the very non-Gaussian directions in your data, they look like Gabor filters. You can also look at this dynamically. Okay, so you can take a deep convolutional network, you can train it with stochastic gradient descent. And here for this experiment, we took kind of three standard deep convolutional networks, AlexNet, DenseNet, and the ResNet. And I'm plotting here the top one accuracy as a function of steps, okay, as a function of training steps. And you can see that, okay, they increase very nicely and they reach kind of state of the art for these specific architectures. What I can now do is I can look at the first layer representations. So I look at the first layer representations that these networks learned, again, through time. And what I'm going to measure is the excurtosis. Okay, so I've given the formula here. This is basically the first measure of non-Gaussianity, right? It's looking at the fourth moment. You subtract the variance. And this is an interesting measure because for a Gaussian random variable, this is 0. Okay, and the more non-Gaussian the distribution gets, the higher this value becomes. Now, if you measure the statistic for these first layer representations, you find something that looks like this. Okay, so in the beginning of training, this excurtosis, it's not quite 0, it's a little bit higher. That's because of finite size effects, because the initial weights of the neural network are not quite Gaussian. But still, this distribution is close to Gaussian. This representation is close to Gaussian. Until after about 1,000 steps, there's a kind of very sudden transition, okay? And in this transition, the neural network suddenly learns representations that are very non-Gaussian. And then it levels off again. And you can see that the onset of this learning of non-Gaussian directions is actually very interesting because it roughly coincides with the moment in which the neural networks actually start to have non-trivial performance. That's where they actually start learning something. And it's also the moment in which these receptive fields fall. Okay, so here are the receptive fields again of the first layer for the DenseNet, but it's the same for the AlexNet or for the ResNet after about 100 steps. And you can see that they're still very close to initialization. Nothing much has happened. But after 10,000 steps, so after the sudden increase in the non-Gaussianity of the representations, you can see that these receptive fields have undergone a kind of localization transition, right? You can see sort of the seeds of the Gabor filters emerge here. We have the localization, we have the orientation, and then for the rest of training, these features become a little bit sharper, okay? But I would say that the seed is really planted in the sudden increase in non-Gaussianity of the representations, okay? Are there any questions on this part so far? Okay, I don't see any right now.
Can I?
Yes,
Well,
please.
probably it's obvious, but
Yes.
the reason you disregard skewness is probably you have some orientational symmetry in the whole system problem.
Exactly, yeah. I could have looked at skewness too. That would have been kind of related to the third moment, right? That would have been the third cumulant. Here I'm looking at the fourth-order kurtosis because later in some of the data models that we're going to use to reproduce this theoretically, we're going to have a point symmetry, and so the skewness will be 0. So that's why I'm
Yeah,
looking at the kurtosis here. But it's purely
I see.
convenient. It's a good point, though. Any other
Thanks.
question? Okay, great. So then I guess the point that I've tried to make here in the first couple of slides is that, okay, neural networks, they kind of learn the features that are important to them by themselves, right? They just learn them directly from data. And these features, at least for images and convolutional neural networks, they really seem to be shaped by the higher order correlations of the data. But if you start, okay, that's an observation. If you start thinking about this now, you might wonder as a theoretician, okay, how hard is actually this task, right? So how much data do I need to learn from higher order correlations? How much time do I need? And then, you might start getting a little bit confused because learning from higher order correlations from a computational point of view or statistical point of view, these are actually hard problems. Okay, so the simplest model for learning from higher order correlations is probably something like a tensor PCA. Okay, so I give you a d times d times d, etc. tensor, for example, the 4 for the cumulant tensor. And then I want you to decompose this. I want to find the best rank 1 decomposition, right? That's kind of a generalization of PCA to a tensorial object. And I think the first paper that kind of studied this from a statistical point of view that introduced this model was this newest paper by Richard and Montanari a couple of years ago. If you want to do this by SGD, which is not necessarily the best algorithm, but it's the algorithm that we care about, right? Because that's how we train neural networks. This is actually a hard problem. There was a recent analysis by Gérard Benarous and collaborators who showed that if you do this with online stochastic gradient descent, time it takes to recover this first principal component scales like the input dimension to the order of the tensor minus 1. So for a 4-order cumulant, this would be cubic in the input dimension, okay? And that's a long time. If you're dealing with high-dimensional inputs like images, really that's just too expensive. And this is just for the 4-order cumulant, right? So I'm not even talking about the higher orders. So we started thinking about this and we started wondering, okay, so how do neural networks do this efficiently, right? So maybe it's got something to do with the fact that we're training them on a supervised task, right? We're not training them on an unsupervised tensor decomposition problem. We're training them on a supervised classification task. So we cooked up this little model that we call the spiked cumulant model. It's a binary classification task. In one class, you have just Gaussian IID vectors as your inputs. Okay, so these inputs are completely structureless, if you will. Whereas in the other class, inputs are spiked. Okay, so they're generated by this particular equation. So they're a Gaussian noise vector plus this spike u, which is fixed vector, okay, times the signal to noise ratio beta and a kind of latent scalar variable g that's a Rademacher variable. For those of you who know a bit about random matrix theory, this is a bit like building up a random Wishart ensemble, a spiked Wishart ensemble, except that the latent variable now is non-Gaussian. Okay, and in fact, what we're going to do in the second step is we're going to whiten the inputs. Okay, so what does that mean? That means that if I give you this data set, you look at PCA, you look at the second moment of your inputs, you don't find any feature. The covariance of the inputs in both of these classes is the identity. Okay. Also, if you project this kind of data in both classes along a random direction, okay, so I take a neuron with a random weight, okay, in almost any direction, the distribution of the projection, so distribution of W times X, it's just going to be a standard normal distribution like the one I sketch here. Except there's one direction that I've hidden here in input space, is this direction U. Because if I project along U, I get this bimodal distribution, right? Because if I project along U, what I'm really looking at is this binary random variable G with some noise. So I get this noisy bimodal distribution, okay? So if I want to distinguish these two classes, I need to find this direction U. But that's a hard task because when high dimensions, and there's only one direction, which is sort of non-trivial. This is similar in sort of spirit to models that people have looked at under different names in different contexts, independent component analysis. There's this nice paper by Yue Lu from a couple of years ago. Non-Gaussian component analysis is a field that has seen a lot of activity in the last couple of years. And so, yeah, this is one instance of such a model as a binary classification task. And it's everything clear about this this task. So I need to solve this binary classification task. I can only do it by finding this one direction, which is encoded in the higher order correlations, not in the Gaussian fluctuations, right? So PCA here is useless.
Can you hear me, Sebastian?
Yes, I can hear you.
Just a quick question here. So you do this binary classification on the noise and the one that you generated from the spike model, but then right after you do the whitening. So then you kind of have the covariance back again, like white.
Exactly.
And this way you try to differentiate with, let's say, higher order moments of the two data and try to classify among the two.
That's exactly right. By whitening the data, I force
the non-Gaussian setting there, therefore.
Exactly. So that's exactly right. By whitening the data, I force any algorithm that can distinguish these two inputs to look at the higher order correlations, right? You cannot cheat here. You cannot just look at the covariance and do something clever like PCA. You have to look at the higher order correlations. And that's the whitening here is the key step.
Gotcha. And do you have any assumptions on the scalings here? Like beta or other scaling?
So the scaling is such that, okay, so this is the Spite-Bichat scaling in a sense. So the beta would scale as 1 over the square root of d. And both the number of samples and the dimension go to infinity, okay? And I keep the number of samples and the dimension proportional to each other. And then I ask essentially, okay, how much data do I need to recover?
Oh, okay, thank you.
No problem, good question.
Also,
yes.
Regarding the previous slide, you showed us the data for kurtosis, but in the high dimensions, you have, again, fourth order terms like xi square, xj square expectation. So, I mean, it was just an example, I assume that, right? I mean, you will eventually take into account these kind of, mixed higher order terms.
Yeah, exactly. So they play into this too. I'm not going to show this explicitly on the slides, but yeah, in the calculations, you have to take into account all of these indices. Yeah.
Thanks.
Cheers. Okay, so how hard is learning in this model? This is really a question about how many samples do you need to solve it. Okay, and the way to analyze this, or the way we chose to analyze this together with my student Lorenzo Bardone here at CISA, was to look at the norm of the likelihood ratio. Okay, so the likelihood ratio is a very classical object in statistical testing, right? And in these high dimensional settings, you can show that if the norm of this likelihood ratio diverges, this is let's say, good indication for the fact that these two distributions become distinguishable. Okay, so that you can solve the task. Here, in this particular case, we were able to show essentially by direct calculation, you can prove that the likelihood ratio will diverge for a number of samples that's linear in the input dimension. Okay, so that's nice. That's a number of samples that's really reasonable, if you will. But this is an information theoretic result. Okay, so this basically assumes that you have as much time to do the statistical testing, to do the computation as you want. And in particular, this time will be probably exponential in the dimension, right? So this is really not an algorithmic result. If you want to know what you can do with a polynomial time algorithm, instead what you need to look at is the low degree projection of the likelihood ratio, okay? So this is a bit more work, but Lorenzo plowed through. And in particular, what we looked at is the LDLR for a degree that scales like the logarithm of the input dimension. That's important so that you capture also spectral method, these kind of things. You cannot compute the likelihood ratio anymore, or the norm of the LDLR, but you can bound it. So we have matching lower and upper bounds. And to make a long story short, what you can show is that this low degree likelihood ratio, it will diverge for a number of samples that's quadratic in the input dimension. Okay? So in other words, you only need a linear number of samples if you have unbounded resources. That's nice. But if you want to finish this task, before the end of your PhD, you'll need a quadratic number of samples if you want to do it in polynomial times. And this is just for, like I said, the fourth order cumulant, which is informative here. This is not even thinking about the higher order correlation. So again, really, for high dimensional inputs like images, this is just too expensive. But this is the best that you can do according to this LDLR analysis. We then use these results also to benchmark some different algorithms. So you can use this now to benchmark neural networks, for example, random features or kernel methods to see sort of which algorithm does better. We can discuss this over questions if you're interested. To make a long story short, this was work with Federica Gerace and Esther Scheckel. The lazy learning regime here fails. Okay, neural networks are efficient at learning this task, so they saturate the bounds from the lower degree likelihood ratio, but kernels don't. They need more data, and this is another example of this failure of lazy learning that's been discussed in many different contexts. For example, in this nice paper by Léonique Chézard and Francis Bach, and later on by other groups, Montanari's group. We had some works on this, etc. I don't want to go into too much detail of this looking at the time. Instead, what I just want you to remember from this analysis is that learning a single non-Gaussian direction is a hard problem. Okay, it takes a lot of data if you want to do it in polynomial time. But we saw previously that the neural networks, that's exactly what they do, right? They learn these features from the higher order correlations. We saw it by the ICA, we saw it by looking at the kurtosis of the representations. So that begs the question then, how do neural networks actually learn these higher order correlations efficiently? Okay. So what's a good model for this? And to think about this, we actually went back and did some experiments, and we got a nice idea from one of those experiments, which was in this paper with Maria Refinetti and Alessandro Ingrosso. So in this experiment, we basically took one of those convolutional neural networks, okay, a dense net in this case. It's called dense because it's got dense skip connections between all the layers, so it's a convolutional network. And we trained it on Cypher 10. Okay, and then as you do that, again, we're plotting the test accuracy here as a function of training steps, as a function of training time. If you do this on Cypher 10, that's the kind of curve that you get. But now if you wonder, okay, what did the neural network actually learn from the first two cumulants of its distribution, right? What did it learn from just the mean and the covariance of, let's say, the images of horses, the images of frogs, and so on? To test that, we built a Gaussian clone of this data set, okay? So we took one Gaussian for each class, so it's a Gaussian mixture, and then the Gaussian for each class, we fitted its mean and covariance to the images in that class. And then we sampled a new data set from that Gaussian mixture. So the first image here at the top, image I should say, is a sample from a Gaussian that has the same mean and the same covariance as the horse images of Cypher 10. And on the bottom, you see a sample from a Gaussian that has the same mean and covariance as the frogs in Cypher 10. Now I can train my dense net from the same initial condition on this Gaussian mixture and test it on Cypher 10. Okay, and then I get the following curve. So if you look at this curve at the end of training, the performance on the original images is much worse now. And that makes sense, right? I've essentially removed all the higher order correlations from each of the classes of Cypher 10. I've removed a lot of information. So if you don't have that information, you're going to do worse on Cypher 10. Right? That makes sense. What I found surprising when I first did these plots is that if you look at the beginning of training, these two curves actually exactly overlap. Okay? So in other words, for the first 20, 30 steps of SGD training, the neural networks does not see the difference between Cypher 10 and the Gaussian mixture. Okay, so in the beginning of training, the neural net actually only looks at the mean and covariance of its data. And later on, it sees, there's actually something more going on here in the higher order correlations. Let me extract information from that too. But that suggested to me that there's some kind of sequential learning going on here, right? First through the Gaussian and then through the higher order correlations. In fact, I now think that this is a very general principle. In this paper, we also analyzed this with other types of clones of the images. We've recently extended this to natural language. So we see something similar. If we train a transformer to predict the next word in Wikitext, we see that it first learns kind of 3-body correlations and 4-body, and then the full distribution. I come back to this at the end of the talk, right? But the key idea here is that somehow neural networks seem to be going through their data distribution in a kind of sequential way. Okay, they seem to be learning increasingly complex distributions over their data set. And so we thought, okay, in this bicumulant model, there was no Gaussian fluctuation, right? We whitened the data. So maybe we should put back some Gaussian fluctuations and let the neural network kind of learn this distribution in a sequential way. And that was kind of the key idea in this second paper that I want to discuss, sliding down the stairs, again with Lorenzo Bardone. So here we were basically inspired by this previous experiment, and we tried to cook up a theoretical model that could account for this very quick learning of the higher order correlations, right? And so the model that we came up with, we call it a mixed cumulant model. It's essentially a version of the spiked cumulant model that we had before. Okay, it's a binary classification task, supervised. In one class, you again have just Gaussian noise vectors that I'm calling W here. In the other class, you have, again, spiked inputs. Okay, so in red, I'm showing you, again, the spike that's in the cumulants. Okay, but I'm adding two more spikes here. I'm adding essentially a mean. That's the spike called M. And I'm adding a spike in the covariance. That's the spike called U. Okay, don't worry so much about the formula. They're really just for fun. Think about what this data looks like if I'm taking projections of it. Okay, so if I take any kind of projection, any direction of the Gaussian data, I get this black probability distribution. I just get a standard normal distribution. But if I project my spiked inputs along the M direction, along the mean, I get a Gaussian in the projections, but it's shifted, right? Because this tells me that this data has a non-zero mean. And by projecting along that mean, I get this shifted Gaussian. Likewise, if I project along the U direction, that's the direction in the Gaussian fluctuations, that's looking at the second moment. Okay, and if I take my B1 big enough, what you'll see is again a Gaussian distribution for my projections, but it's wider, right? Because here I've essentially added some variance in one particular direction. I called it U, and so if I project along that direction, I get a very wide distribution for my projections. Okay, and then finally we have the cumulant that we hit, the spike, sorry, that we hit in the cumulants. If I project along this V direction, I get this bimodal, very non-Gaussian distribution for my projections. Okay, so in other words, there are three different directions here that help me discriminate these two classes, M, U, and V, and then coded in the mean, the covariance, and the higher order cumulants of my data. Okay, now I can train my neural network and I can see what it learns. Okay. So if I run this two-layer neural network now, I get this red curve for the test error. Okay, you can see there's an initial exponential decay, a plateau, and then a second decay. This first decay is related to learning the mean. We see this by actually evaluating this neural network on data that has only the spike in the mean and not the others. And you can see that in the beginning of training, these two curves overlap. But then very quickly, the neural network realizes, there's also some structure in the covariance of my data. And so it learns the second spike. And that's the point where it hits this plateau here. And you have this overlap between the green and the red line, right? So the red is the test loss on the full data set. The green is the test loss on only the Gaussian parts of the data. And you can see that they overlap for a very long time. And only after a long time, 10 to the 7 steps here, does my neural network realize, actually, there's a third direction here. It's hidden in the higher order correlations, and I'm going to learn that too now. So in some sense, this is nice, because we see an example here in a controlled setting of this learning of distributions of increasing complexity that I showed you in this experiment before, and that also other people have observed now in different contexts, in energy-based modeling and in autoencoders. Belrose et al. Did it also for some transformers. But there's one problem here. And the problem, you can see it if you compare the result on the synthetic data to Cypher-10, right? The problem is that it takes, again, a long time to learn the non-Gaussian correlations, right? You have all of this plateau, this is logarithmic in the steps, right? So you only learn the non-Gaussian correlations after some 10 to the 7 steps. Later on, in a couple of slides, I'll show you rigorously that this is, again, this sort of cubic scaling with the input dimension for the fourth order cumulant that we wanted to avoid. And that's showing up its ugly head here. If I look at Cypher-10, on the other hand, you can see, first of all, that the loss is just a continuous decrease. Okay. And furthermore, you can see that the neural network quickly accesses the non-Gaussian part of its data after about 1,000 steps. So what's missing here in in the data. Somehow in our data model, what we're missing is a simple way for the neural network to use the Gaussian information to jump to the higher order correlations, right? We're missing kind of a step here. These two things are not connected. So the sequential learning takes a long time. So what's missing here? So we thought a little bit about it. Essentially, what we want is we want to be able to infer something about the non-Gaussian part by knowing M and U, right? So one thing we thought about is what if these directions have some finite overlap, right? So here, U, V, M, they're all orthogonal to each other. What if they had some final overlap? Would that help me? And it turns out it doesn't. You can see it experimentally. You can see it with the theory that I'm going to show you in a couple of slides. Really, what you want to do here is you want to change the distribution of the latent variables. Okay, so the latent variables here are these variables G and H. They're the scalar variables that basically tell you what the distribution of the data looks like if I project along U or V. In this experiment so far, I was taking these two latent variables to be uncorrelated. Okay, I just drew a Gaussian latent variable, and then independently of that Gaussian latent variable, I drew a binary random variable H with equal probability plus or minus 1. If I correlate them now, things change a lot. Okay, so here's the same experiment on the same synthetic data model, but now for correlated latent variables. So in fact, I'm taking H as the sign of G. Okay, so H is now just the sign of the Gaussian latent variable. That means that marginally it still has the same distribution, right? It's still plus or minus 1 with equal probability, but it's correlated. If I know G, right, I actually know exactly what H is, or the other way around. If I know H, I can constrain the distribution of G. And if we train on data in this way, we get this final plot. And this is now very nice because this now shows one single exponential decay of the loss, or single power law decay of the loss. Okay, there's no plateau, and the neural network accesses the non-Gaussian part of its data very quickly. Right? You can see this here. The test loss on the full data, the red line, it quickly diverges from the test loss on just the Gaussian part of the data. So very quickly here, the neural network accesses these higher order correlations without having this long plateau in the test loss where nothing happens. So this is a bit of a loaded slide. So maybe this is another good point to pause for a second and ask if there's any questions on what we're doing here or what we did here.
May I ask
Yes, please.
a general question?
Yes.
In this case, you are basically using the cumulative expansion as one way of expressing the increasing levels of complexity in your data.
Exactly.
But one could, in principle, use other kinds of expansions, right? I mean, to capture the complexity. I don't know. I mean, you have Chebyshev expansion, I don't know, Hermite expansions and stuff like that. I wonder if you would see the same kind of thing if you used something else.
That's a really good question. So it's actually funny that you mentioned Hermite expansions here. Because, okay, I didn't mention it, but on a technical level, Hermite coefficients are really important here because on a technical level, to analyze the dynamics here, we're again going to have to expand the likelihood ratio between the spiked data and the Gaussian data. And since your null hypothesis here is a Gaussian, a very natural basis to expand these things is our Hermite coefficients, Hermite polynomials.
Yeah, we're both physicists, I guess.
Yeah, exactly.
We understand.
Yeah. Exactly. So yeah, so your intuition is exactly right. So in this case, there's this nice sort of correspondence between this cumulative expansion and the expansion in Hermite polynomials. But there are other expansions that you could think about. I think these are very sort of cumulatives are very natural, but also a little bit sort of brute force, right? What we're thinking about now is expanding in different bases, especially for images, for example. Wavelets are a natural thing to think about, like query modes. So that's something that we're thinking about right now.
Thanks.
Pretty good question. Any other questions here? Okay, very good. So I guess phenomenologically, what I'm trying to tell you here is that what allows neural networks to learn higher order correlations efficiently, at least in this model, is some kind of correlation between the latent variables, right? So in some sense, the directions may be independent, okay, but somehow the projections of the inputs along those directions, they have some correlations, and that allows you to quickly jump from the mean and the covariance, from the Gaussian correlations to the higher order correlations, even though that's in itself a hard computational task. You can make, this was experiments, you can make this whole thing rigorous. In this paper, we did this for single neuron, for perceptron, spherical gradient descent. I don't want to go too much into the details here. Let me just say that many of the classical tools in statistical physics that we like to analyze these systems, they break down here, right? So there's some very nice classical work now from David Saad and Sarah Soller in the 90s who derived some kind of closed system of ordinary differential equations that describe the dynamics of neural networks trained using stochastic gradient descent. That work has triggered a lot of recent activity in the last couple of years, but it crucially assumes that inputs are Gaussian. Okay, so this theory here, it breaks down because our inputs are by construction non-Gaussian, right? These Gaussian assumptions, they actually go much further than vanilla Gaussian inputs, okay? So a lot of recent work in the last couple of years was on these topics of Gaussian equivalence, right? This idea that for many purposes, even realistic data sets, you can hide the complexity way behind an equivalent Gaussian model for the data and then do calculations on that Gaussian model that match the simulations on realistic data, right? I'm giving a couple of references here. But again, this assumes that somehow under the hood something is Gaussian, in this case, the projections. But here the projections are also non-Gaussian by construction. Okay. So instead, what we have to do is we have to give up essentially on having a closed form solution to the system. Okay. But what we can do is we can do kind of stability analysis. This is a technique, an approach that was introduced in a recent paper by Benarous. And for Gaussian inputs, and here we extended this technique to this non-Gaussian case. And if you do that, if you carry through with the calculations, you can essentially show that if you only have a spike in the higher order correlations, the number of samples will be cubic to learn it, okay? If you have correlation between the latents instead, you get essentially linear sample complexity. Okay, so you get fast learning. There are some factors of log that I'm hiding under the carpet here at the bottom right because I wanted to show you this little picture of the guy who's running up the staircase and who's very happy. Okay, so again, I don't want to go into the details of this in the light of time. Let me just say that you can basically prove the timescales over which you learn these things in this simple model, and they match what you see in those simulations. Okay, you can then look at this a bit more in detail, different scales of the learning rate, etc. Let me also finally say that people have looked at staircases in the context of teacher-student models, so Gaussian inputs and some non-linear target function they're trying to learn of them. I'm citing a couple of references here. I've probably missed quite a lot. Let me just say, as one important distinction between these teacher-student models and the spike cumulants that we're looking at here is that teacher-student models are, in a sense, easy. Okay, so you can learn them with essentially linear sample complexity, for example, by doing multipass SGD. There was this very nice paper from Yatin Dandi and colleagues in the group of Florent Jacquelin and Lenka Steborova who showed this numerically and using some dynamical mean field theory. Here, on the other hand, these mixed cumulant models, they're intrinsically hard, right? The likelihood degree, the LDLR ratio analysis showed us that this is a fundamentally hard problem. Like you can do multipass SGD and it's not fundamentally going to change the difficulty of the problem. Okay, so with this, let me just say that correlated latents are a mechanism that help you learn features from higher order correlations. We're doing some experiments right now with real data where we try to sort of extend these ideas to sort of show this also on real images. This is work in progress. But what I haven't talked about yet, and this is the last point that I wanted to mention, is okay, very nice. You learn features from higher order correlations. You can learn them efficiently if there's correlations between the latent variables. But why do they look like this? Why do the filters that you learn at the end look like these Gabor filters? Why are they localized? Why are they bandwidth oriented, right? So what is their shape and how does that come from properties of your data. Let me just check how much more time do I have?
15. Sebastian.
Sorry, 15 minutes?
Yes, 15 minutes.
Okay, I'll need a lot less than that. But great. Okay. So this goes back to some work that I did together with Alessandro Ingrosso that we published 2 years ago. And with Ale, we were also wondering about nice models for feature learning on images. Okay, so nice model of images where we can train neural networks and learn interesting features from. And so as we thought about what would be a good model for images here, right? So there's many wavelet models, texture models, and all these kind of things. We wanted something that's even simpler, okay? And something that really just obeys two fundamental properties that images have, okay? The first is translation invariance, right? Images are roughly translation invariant. That's why it's a good idea to use convolutions, etc. So here what we did to get translation invariant data, okay, we took some Gaussians, mean zero, and with a covariance that is this exponentially decaying kernel, okay? So the key point here is that the covariance between any two pixels only depends on their relative distance to each other. And then you have some kind of length scale psi. Now, if you draw an input from such a distribution, it looks like this, right? It's this typical Gaussian field. It's kind of very blurry, right? It really doesn't look much like a real image in many ways. One important way is that it doesn't have edges. Right? One really important property of images is that there are edges. There are sudden changes in luminosity, and they help us kind of segment our surroundings, right, into objects. I have this laptop in front of me. There's a sudden change in luminosity as I see the background of my desk, etc. And this is an old topic in sort of vision sciences, right? So here's a nice old neurosphere from I think 97 by Anthony Bell and Terry Sejnowski, in which they really say that edges are actually the independent components of natural scenes, so really key ingredient. So how do we get edges into our Gaussian random fields? Okay, one really simple way of doing that is just to take our Gaussians and to feed them through a saturating nonlinearity. Okay, in this case, we took the error function because it gives you nice integrals under the Gaussian measure. But really, the key point here is that it saturates. So for large values, it goes to -1 or +1. And then we have this little gain parameter g here. This is a scalar number, and it really, what it does is it controls the slope of this error function around the origin. So in other words, it determines how steep, how sort of, sharp the edges in our images are. Okay, so if I increase this gain, okay, and I feed this Gaussian field through the error function, this is what I get. I get images that have increasingly sharp edges. Of course, from a statistical point of view, what I'm doing here is I'm turning on the higher order correlations, right? As I put the Gaussians through this error function, it's a nonlinear function, I get non-trivial higher order correlations. And in fact, relatively speaking, these higher order correlations become more and more important as the gain increases and the edges get sharp. Okay, so now I have a very simple data model. It's translation invariant, it has edges. So, okay, let's see what neural networks actually learn from it. To do that, we built this very simple binary classification task where we asked the neural network to discriminate images with short and long range correlations, okay? And to our great surprise, if you take now a simple, fully connected two-layer neural network and you train it to discriminate these types of images, what you find after training is that the neural networks, they learn a very particular receptive field, okay? In fact, half of the neurons, their weights are roughly oscillatory. They don't really look like much. But the other half of the neurons have localized receptive fields, right? So all of these little pixels in these little squares are a single weight of one of the hidden neurons. So here I'm showing 8 hidden neurons. 4 of them are localized. Localized in the sense that most of the weights, most of these little pixels are dark blue, and that's a value close to 0, okay? And only a couple of them are actually very large. And they are kind of clustered together in this nice spherical pattern. Now, this localization is a very non-trivial effect, right? In a sense, what we've learned is a very simple convolution with a single filter. So a single convolution with a single filter, and the fact that this filter is kind of spread out like this over the receptive fields means that you're essentially tessellating the whole of input space. So this simple fully connected network, it essentially learned a convolution from scratch. This is a very non-Gaussian effect. If you repeat this experiment on a Gaussian clone, so a Gaussian mixture that has the same mean and covariance per class, you don't get this behavior. You get, again, the high-frequency oscillating neurons, and then you don't get localized neurons. You get neurons that look a little bit like Fourier components, right? They look a little bit like 2D outer products of Fourier components. And indeed, if you look a bit more closely, that's essentially what they are. So this got us very interesting, right? So one of the key points of the Gabor filters is also that they're localized in space, right? And here we kind of learned these localized receptive fields directly from this non-Gaussian data model. So why is that? Why do receptive fields localize? Why do these features look the way they do? You can understand this again by looking at the fourth order cumulant of your inputs. And here we had the question earlier, right? You really have to look at this object with all of the indices, right? This is a fourth order tensor. And what you can do with such a tensor is you can again look at its principal components. Okay. And the idea for that is because in the previous slide, we saw that on the Gaussian data, you essentially learned these oscillating receptive fields, right? They were essentially Fourier components. Now, Fourier modes are, of course, the eigenvectors of the covariance of translation invariant data, right? If you have a translation invariant data, the covariance matrix is what's called a circulant matrix, and you can diagonalize that exactly in the Fourier basis. So from the Gaussian data, the neural networks essentially learned some kind of principal components. We thought, okay, maybe on the non-Gaussian data, you learn again some principal components, but not of the Gaussian covariance, but of the higher order correlations, of this higher order cumulant that we already saw on the third slide or so. So let's look at the principal components of this tensor. If you look at this for blurry images, so images that have a small gain, that have very sort of unclear edges, what you'll find is something like this. So the gray lines are the first 10 leading principal components of this tensor. And as you will probably agree, they're a bit of a mess, right? They're kind of oscillating, they're going up and down. It's really hard to see any kind of structure here. And this seems important because likewise, also the weights of my neural network, they are just oscillating like this. Here, I'm showing you one example of such a weight in blue. But then something very interesting happens when you turn on the non-Gaussianity. So if you increase the gain, if you make the edges in the images sharper and sharper, okay, if you make the higher order cumulants more and more important, there's a very sudden transition. And beyond that transition, all of a sudden your CP factors look like this. So they localize in space, they now have this very nice bump form, and they kind of tessellate input space. Okay, they kind of spread through input space. And that transition in the sort of eigenvectors of this tensor, that transition in the principal components of this tensor is important, okay? Because as the as the CP factors, as the principal components of my tensor localize, so do the weights of my neural network. Here again, I'm showing you just one example of such a weight in blue, and you can see that it also localized in space. And this, we think, is a direct consequence of the translation invariance of the data. In fact, you can see that the width of these localized receptive fields, of these localized principal components, it's linear in the correlation length of my images, right? So you have this very nice, let's say, connection here between the symmetry of my data, translation invariance for the images, the properties of the higher order correlations, they localize in space, the principal components, and the weights of the neural networks, which kind of learn these principal components and also localize in space. Okay. What I also find interesting is that if you look at this transition numerically here on the y-axis, I'm showing you a measure of localization of these principal components, the inverse participation ratio. If it's small, the vector is kind of all over the place. If it's large, the vector is nicely localized. And as I increase the effective dataset size, right, you can see a kind of transition here in this localization. To me, this is a little bit reminiscent of transitions that we know from random matrix theory, right? Those of you who know maybe the BBP transition in the Spike-Bichette model, right? You get this similar behavior. Here, we get also this movement of the lines as we increase D. So it's not quite a phase transition. I think that's an artifact of using the error function. I think if you had just used the polynomial here, you would get a very clean and very clear phase transition. Okay, but so in other words, there is some kind of interesting phase transition, I think, here in the principal components of this tensor. I'm not aware of any kind of theory that could capture this. So I'm just putting it out here for those of you who know random matrix theory and maybe you have an idea of how to describe this theoretically. Okay. With this, let me conclude, and then we can have time for a couple of more questions. So what do neural networks really learn from their data? What I've tried to argue is that at least the early features in deep neural networks, they're really shaped by the higher order correlations of their inputs, right? And we can see this experimentally in many architectures. This raises the question of how you do this efficiently. Okay, how do you access this information efficiently? And I've showed you one mechanism by which neural networks might be able to do that, which is correlations between the latent variables connected to the Gaussian and the non-Gaussian part of the data. If you have those correlations, neural networks can learn quickly. And right now we're trying to establish this also in real images, and sort of the first results are quite encouraging. Now, I've talked a lot about image classification here, supervised learning, because that's kind of the setup that we've mostly looked at in theoretical work, right? That's also when deep learning basically had its big first breakthrough. But more recently, the most interesting breakthroughs, they have come in slightly different fields, right? Self-supervision is an important keyword here. That's behind these generative models, both for images, diffusion models, and of course for languages in the form of transformers, right? And so I think one really important challenge for the future is to try to understand what neural networks learn from text in this transformer kind of setup, right? So how are neural networks able to pick up the grammars of a language, for example, from purely statistical information, right? The occurrence of words in admittedly a lot of text. I think that's a really exciting frontier for research in the future. It's something that the community has also gotten very interested in right now. I started looking at this a little bit with my student Ricardo Rende, postdoc Federica Gerace, and Alessandro Laio here at CISA. Okay, I'm running out of time, so I just want to say that part of this work, for example, was establishing that also transformers show this learning of distributions of increasing complexity. Right, this is the plot that I showed you in the very beginning, and I promised I would come back to this at the end. I don't have time to go into the details of this, but the paper just came out. I'm happy to talk about it offline. And again, there's lots of other interesting works coming out from the community on this. At the moment, I think this will really be sort of a frontier over the next couple of years. It's really a formidable challenge. So with this, let me thank again the students and collaborators who contributed directly to this work. Let me also say that if you like this kind of work, we're hiring PhD students. I also have some postdoc openings in the near future, in the coming months. So please feel free to reach out. I'm attaching here a photo from the view from CISA, and Trieste, you're also welcome to visit in person. And that's all I wanted to say. Thank you very much.
Thank you. Thanks, Sebastian.